This is Professor Thompson. I'm going to do some examples from 4-5. The first one I'll do here is number 6. So I want to find the minimum distance between, the minimum vertical distance between these two parabolas, x squared plus 1 and y equals x minus x squared. So notice that x squared plus 1, that's a smiling parabola. And x minus x squared, if I factor out the x, that has zeros at 1 and 0. And it's a frowning parabola like this. So I'm trying to find the minimum vertical distance. Well, the vertical change is really just the difference in the y values. I had to do all that because I have to see that x squared plus 1 is higher. So that means that the distance here is going to be x squared minus 1, that's the y value of, plus 1, that's the y value of the top one, minus the y value of the bottom one. I have to subtract the entire thing, so you got to be careful. So this is x squared plus 1 minus x plus x squared. So that's 2x squared minus x plus 1. So let's go ahead and write that on the next slide. So this is 2x squared minus x plus 1, and now I want to take the derivative. So I get d prime, and this is 4x minus 1. So now, if I set that equal to 0 to find critical values, then I get x equals 1/4, and note that the derivative is a line, and so it's got 1, 0 here, and it's negative beforehand and increasing, and positive afterwards, so the function is decreasing then increasing. That means that's a local min, but it's also, because it's the only critical value and it has that property, it's an absolute min. It's not always true, but it is in this case. So x equals 1/4 is the place where it happens, but that's not what they asked for. They asked for the minimum vertical distance. So I got to actually go back to d and plug it in. So d of 1/4 is 2 times a 16th minus a 4th plus 1. So that's 1/8 minus 1/4 plus 1, which is minus 1/8 plus 1, which is 7/8. Alright, there you go. Okay, let's do another here, and this is, I guess I'll go backwards a bit. This is 3. And it says, find two positive numbers whose product is 100. So we'll call them x and y. And they're positive, and their product is 100. And their sum is a minimum. Well, I'm just going to put this in terms of x. So y is 100 over x, which you can see from this equation up here. So now I have something in terms of x that I'm trying to minimize, so I take the derivative and I get 1 minus 100 over x squared using the power rule for minus 1. And so now I want to do common denominator just to check where my critical values are. So let's go to the next slide. So this is x squared minus 100 over x squared. And the critical values, well, let's factor the top. It's x minus 10, x plus 10. Put out a space there. Over x squared. So the critical values are 0 from the bottom, minus 10, and 10. But we need x to be positive, not even 0, so we can throw those out. So the only critical value is 10. So our domain is restricted at 0, but that's as far as it's restricted. So we need to look from 0 to 10 and 10 to infinity and show that the derivative is one sign before and one sign after always in that region, and then check that it fits our min or our max. So if you start with, say, the test value of 1, you'd get a positive, and a negative, so you'd be negative. And if you started with 11, this would become positive and you'd be positive. So that means that your function is decreasing, then increasing. So destroying, so that's a minimum, and it's an absolute min by the extreme value theorem in this section. So that means that 10 and 10 are the numbers, because if x is 10, so is y. So the answer is 10, 10.